talk about that. What does that mean to us? What that means to us is that the mean batting average in the major leagues is, let me see if I got this working. Okay, mean batting average is 260, right? 260. Okay, the mean, mu, that's for the entire pop. Well, okay, let me ask you this. I'm going to call mu is 260, and the standard deviation is 0.04 or 40. Okay, standard deviation is 40. What do you call these things called mu and sigma? What are those? Got a name for them? They're parameters, right? They're not statistics, right? Because statistics would be, the equivalent in statistics would be X bar and say SD or S, right? What would those be? Those are statistics. These are based on a sample. These are based on a population. I'm going to talk about the entire population of all the baseball players right now. This is their average, batting average. This is their standard deviation of all the batting averages. So I'm assuming that I know, since actually, tell you the truth, this is one of the areas that you actually really do know in a lot of cases what the values for the entire population are. Normally, we don't know that, right? Normally, we're working with a sample because if we wanted to know, what's the number of people who have diabetes in the United States? Well, gee, not everybody's been tested. We really don't know. We don't have that data. What's the average weight of everyone in the United States? Well, there's no single place to look for that. We rarely know the information about an entire population. If we did know that all the time, we wouldn't need statistics because we know what the numbers are. So literally, we're almost always working from a sample or samples. Okay, so for the time being, though, as we examine this, I'm going to work with some populations. Now, any place else that we work with a where we have information about the entire population? When we don't work with statistics, we work with the entire population. How about what's that? Endangered species? Yes, 12. There's 12. There's 12. Yeah, yeah. Let me give you a hint. We do it every 10 years. Right. That's the census, right? Census, we actually know what the average. We can calculate what the average family size is because we count every family. In fact, there's always a big debate every year about certain portions of the population, say illegal immigrants and so on and so forth, are undercounted in the census because they avoid census takers. They specifically avoid government workers and census takers, as a precaution or out of fear. And they're undercounted in areas where they tend to live. So you would say to yourself, well, gee, since we know they're undercounted and we have a rough idea how many are, why don't we just adjust the census to make up for that undercount? Well, the census is actually part of the Constitution. It's part of the original Constitution. It has to be a physical count. Short of a amendment to the Constitution, right? You can't use information that's based on statistics. You actually have to do a real count, even if you know the count is not accurate. Even if you know that you might be able to improve that statistical count. Okay, so let's take a look at this. So the standard deviation is 40. Okay, so if I were to pull out, if I were to say, gee, what's the probability that I would pick out an individual baseball player at random, right, and that his batting average would be between 240 and 300. 240 and 300. Okay, what do you think the probability is there? How many standard deviations? What's that? 220. That's 220. Yep, 220 and 300. Right? So what's the probability? Roughly 68%, right? What's the probability that what's the probability that it would be between, say, let's see, what's it going to be, 180, right, and 340? Right? What's that? That's 95%. That's our empirical rule. And we know, of course, that 3 standard deviations, basically the entire population is going to be between 140, right? 140 and 380, right? I think the only person that has hit over 380 in the last like 30 or 40, last 50 years is probably Ted Williams is over here. He's up here, right? But he's one guy in how many thousands of guys, right? And he was the last one, I think, to hit over 400 actually. So at any rate, so we can use this to make determinations about what probabilities are in this population. That's how this normal distribution helps us. What's the probability that that someone would have a batting average in the major leagues of 180 and still be playing? What's that probability that'd be less than 180? That's this area in here, right? We have to determine what that area is. Well, we don't have an empirical rule for that. However, we know that between 180 and 340, it's 95% of the population, right? And how much does that leave? It leaves 5% of the population. Since this is symmetrical, the area below 2 standard deviations and the area above 2 standard deviations is going to be the same. And we know that's got to be 5%. So the percentage of players hitting below 180 is likely to be 2.5%, right? Roughly 2.5%, not exactly, but roughly 2.5%, because this is an estimate. What's the probability that someone would be hitting between 260? Was this 260? 260 and 220. What's the probability that they'd be hitting between two? 34. Yeah, 34%, right? Okay, and so on and so forth. So we can manipulate what we know about this normal distribution from the empirical formula, and we can determine all sorts of other information about the ranges, the probabilities, and so on and so forth for a lot of these different outcomes. Okay, so now it's nice, it's nice that we can do this, but all we've done it for so far is round numbers, 1 standard deviation, 2 standard deviations. If I had told you what's the probability that you would add somebody that had a batting average higher than 320, right? That would be, well, I know it's, it's going to be 50% plus 34% plus what's in here. We don't know what's in there, right? Because we only know information about it. We know it's not, it's halfway up to 2, but we know, we can see this area is bigger than that area. So it's not like it's linear, right? So we need a mechanism for understanding even more about this curve that we call the areas under this curve we call the normal distribution. Okay, so keep holding the wrong one. Okay, so let me see if we, okay, here's a nice ugly equation. Did this come up in the lecture? This come, no? Okay, that number describes the shape of this distribution. Okay, you can kind of like visualize it if a value, this is the x and mu are the values in the mean for a sample, and you can see that, well, if the value in the mean is the same, then this is 0 and this is 0, and you can kind of see that, like, when you get to that 0, things flop around back and forth. In other words, the mean, things move around that mean, get smaller outside of that mean. But this formula, which is relatively complicated, describes this relationship, describes this curve. Since we have a formula that describes this curve, we're not going to talk about how this is derived. Since this formula describes this curve, you can use that formula to calculate any height on this distribution. If you know what the x-axis is, in other words, where the value is, x is on the x-axis, you can use this to calculate the y-axis, the height of the curve, f of x. Okay, since you can do that, well, you can calculate all these areas. Yes?
Is that e raised to the whole thing?
Yes. Yes. So we can use that formula. Problem is, it's a complicated formula. It's not really practical for us to use it for every value. So what happens instead is that they've developed a table which represents something called the standard normal distribution. What's the standard normal distribution? Well, we're going to take a nice distribution, a normal distribution. We'll start from there, and we're going to say this is going to represent all standard, this is going to represent all normal distribution. We're going to call it standard normal distribution. Okay, it's going to represent all the, not really the real values of weight, blood pressure, and so on and so forth, but really the shape of all distribution, really the way the values are spread out in all these distributions. Okay, so this standard normal distribution, we're going to say that the mean for this standard normal distribution is 0. And the standard deviation is equal to 1. And we're going to calculate areas we're going to calculate values for every one of the points for this distribution, heights, and so on and so forth. We know what the height is. We know of all these places. We can calculate the areas that are under them as well. If we calculate enough of these values for the spread or for the standard deviation. Now, if we only calculate a couple of values like this, right, it's kind of hard to estimate it because then we're drawing a straight line. It's not really a curved line, and we're trying to figure out the area. So we really need to calculate these things really close together. That's why you see that interval. What that's doing is it's calculating almost an infinite number of values here in order to determine what the areas are under this distribution. Well, once they've done this mathematically, they put it into a table. And this table is called a z-table. Z stands for standard deviations, the number of standard deviations. So when I ask you what a z-score is, I'm basically asking you what is the number of standard deviations that's represented by that number. So for instance, in our baseball example, let me go back to our baseball example. Okay, if I asked you, what a mess, right? If I asked you, what's the z-score for 260, right? What would you say? 0. It's the mean. What's the z-score for 300? It's 1. What's the z-score for 220? It's -1, and so on and so forth. If I asked you, what's the z-score for the value that we couldn't calculate, which was 320, right? 320, what's the z-score for 320? Right? That's that value there, which is in between these two. Right? That z-score is going to be, oops. That z-score is in here, right? That z-score is, let's see, 320, right? Our mean is 260. Our standard deviation is 40. So 320 is 60 away from the mean. 60 away from the mean. So that is how many standard deviations away? 1.5. That's a z-score of 1.5. If I had asked you for, instead of that, if I had asked you for what's the z-score for, let's see, -1 would have been 220, right? If I had asked you for the z-score of 200, that's 60 below the mean. How many standard deviations below the mean is that? -1.5, right? That's what z-scores are, basically, just the number of standard deviations. Again, we had no way to analyze what that area was, so what that probability is, right? So, but we now have a table that will allow us to do that. Now, there's all sorts of different forms of this. One of the ones I put up on Blackboard that you can download is from a textbook called Agresti and I don't remember, Pavreau, Franklin, Agresti and Franklin. Gestation and Franklin, and this has a particularly nice one because what they do is they actually have two tables, one for the negative z-scores and one for the positive z-scores. Okay, nice thing about this, and what they do is, No, they usually have one table.
Yeah, but the new one.
The new one. The online one. Okay, good, excellent. I'm glad to hear that. Okay, so if we look at this first column represents the z-score, right? So in other words, if I look on the second page, this is a z-score of 1.0. This is a z-score of 1.5. Well, it's not very precise, right? Maybe we want to know to another digit. So to enable it, in order to use these, in order to save space and have just a couple of tables to give us all these values, right, and give us another digit, what they do is that they list the third digit in these columns. So in other words, this would be 1.0. This would be 1.00 right here. This would be 1.00, 1.01, 1.02, 1.03, 1.04, and so on and so forth. So each one of these columns represents the third digit in your z-score. Anybody know what these numbers in the middle stand for? I'll give you a hint. 0, a z-score is 0, 0, 0 is 0.5. A z-score 0 is the mean. That's the area below, and if you look at this little colored area here, it actually shows you that all these numbers in the middle here represents the area of the curve below that value. The blue area is the area below that z-score. So our z-score for the area below a z-score of 0, in other words, the mean is half the distribution, 50%. What were we looking at? 1.5, right? What's the area below 1.5? Okay, so we're going to go to 1.50 is 93.9332, about 93%, right? So 93% of the distribution is below a z-score of 1.5. That leaves how much above? 7% of the distribution. In other words, probability of picking a random person from this distribution and having them and finding out that the z-score for that guy's value is greater than 1.5 is only about 7%. Less than 1.5 is about 93%. Okay, so now the problem here is that when we go below 0, z-score below 0, well, now we're on the other side of the mean. So we have another distribution over here where we can actually read a negative number like that. Negative 1.5 is going to be, negative 1.50 is going to be about 7%, right? Which is, remember, that's the symmetrical, so it's just about what we, but that's the area below that value, that z-score, right? So we can actually use this table to calculate all these different values. The other thing I can use this table for let me get a clean sheet here. Sure.
Are you saying that when you ask what is the probability of having a batting average of 320 is the same as asking what is the probability of having a batting average of 320 or more? Because the area would be the one
No, first,
9.
time out. The probability of having exactly a batting average of 320, right? It may not exist. There may not be anybody in the major leagues right at this moment that has a batting average of exactly 320, right? So, and if you think about it, we're talking about that would be kind of like having just a straight line in the, what's the area of a straight line? 0. So really, that's not really the way we use this table. We use this table to determine what's the area below that value or what's the area above that value. In other words, what's the probability of having a value of 320 or higher or 320 and lower?
What's the y-axis on the cumulative probability?
I'm sorry, say again?
What's the y-axis in this graph?
Oh, the y-axis is it? Oh, that's a good question. That's a good question. The y-axis is that f of x in the formula that we just saw, but it represents. How can I put this? It doesn't really represent. It represents kind of the instantaneous probability,
right,
but it really doesn't represent anything because it has no value. It can't occur. In other words, there is no like absolutely perfect. In other words, what does it mean? It just means a number. It just represents a number.
well,
So it's really the area that we're interested in.
Is there too many events? So
No, it's
like 0?
it's well, think about it. If I asked you what somebody's blood pressure is, right? You would tell me, oh, their blood pressure is 120/80. Is their blood pressure really 120 over 80? Or is it 120.00000000001 over 79.9999999? If I really measure something out to that point where it has no area, it's that straight line, it loses meaning, right? It doesn't really, it's not really something that we can use meaningfully. Okay, so I wouldn't worry about that. You're just looking at that line as a point where you want to determine area below it or the area above it. I wouldn't get too worried about what that actual value means in terms of the z-score. Okay, so for what that's worth. Okay, so I forgot what I was going to say here. Okay, there's another way we can use this z-table. Okay, and that way is, let's say that I told you, here's our mean is 260 again. Our standard deviation is 40. Okay, let's say I said to you, gee, I want to know what the probability, what the value, what batting average I have to be in the lowest 10% of all baseball players playing in the major leagues. Okay, I'm a manager. I'm saying anybody that's in the lowest 10%, I'm cutting them right away. Right? So what does that batting average have to be? Well, I want to know what the z-score is, right? Because if I know what the z-score is, I can figure out what that value is, right? So let me think about this. Lowest 10%. I need to know what z-score will give us a value of 10% to the left of that z-score. First of all, I know it's a negative number, right? Because it's to the left of the mean. If I had asked you for the highest 10%, it would be a positive number because we'd be looking at this value up here, right? This area over here, 10%, right? And that's z-score. They're going to be the same z-scores, aren't they? Because this is symmetrical. One's negative, one's positive. Okay, so let's figure out a way we can use this table. What are these numbers in the middle again? They're areas, right? So we're looking for the z-score, which represents 10% to the left of that z-score. So I'm going to look for the area, which is 10%, right? Or 0.1000. What's the closest I can get to that? 0.10000. Let's see. Here we go. 0.0968. Here we go. This is about the closest I can get to it. What is that? It's 1.28. So my z-score, which represents the point at which below that z-score is 10% of the population, or 10% probability of picking an individual from that area, is 1.28. This z-score here, z, is equal to negative 1.28. Okay, so that means that the batting average that represents the lowest 10%, right? The batting average representing the lowest 10% has a z-score of negative 1.28. Well, I'm going to give you a quick formula here. Z is equal to x minus mu over the standard deviation. Make sense? The difference between a value and the mean divided by standard deviation is the number of standard deviations. When we were doing it before, that would have been, let's see, that would have been like 300 minus 260 over 40 would be 1, right? That's exactly what we did, is apply this formula intuitively rather than as a formula. Let's now use it as a formula. A z-score of negative 1.28 is equal to, I don't know what x is, that's what I'm after, is the batting average that's represented, minus 260 over 40. Okay, multiply both sides by 40, minus 1.28 times 40 is equal to x minus 260. Okay, what is 1.28 times 40? 51.2, right, is equal to x minus 260. Okay, I bring two, am I doing that right? I should have made mu over minus x, right? Nope, I had it right. Okay, I had it right. Oh, this is a minus number. I'm sorry, you fooled me there. Okay, it's minus. Okay, this is going to work now. Okay, x minus 260, add 260 to both sides. And what is x equal to? 208.8. So this z-score of negative 1.28 represents a batting average of 208.8, right? So anybody that has a batting average below that is in the lowest 10% of this population, right? Or another way to look at it is the probability of picking an individual out of this population randomly and having a batting average less than 208.8 is 10%. And we can do this on the high side also. So we can use this table two ways. We can use this table to determine z-scores if we know what the area is, or to determine what area or probability is represented by that z-score, or we can use this table if we know what the area is to determine what the z-score and the actual value is that represents that area. Okay, so pretty good, right? Pretty useful. Okay, so let's put it to work. On Blackboard, there's a document which is a combination of homework and lab exercise. I'll open that up. Let me see if there's something else I got to do. Okay, we're going to get started on this. I'm going to take maybe take a break after a little while, and we'll take a look. I don't know how much we got on binomial distribution here. The two-tailed probability. Okay. I'm going to give you some other examples also because some of these are actually worked out for you. I'm going to tag on to this some other stuff on Blackboard, but maybe you can submit this with the other stuff with the solutions to the problems. We may get through a lot of this tonight. We may not get through a lot of this tonight. Okay, so we're also going to use it. There's another place we can go for this table if we don't have the table physically handy, and that is Excel. Excel has this function or table built right into it. We're going to take a look at how to determine that. So let's start off with the empirical formula. Okay, so I'm gonna assume that the heights of adult Caucasian men have a mean of 68 inches and a standard deviation of 4 inches. Find the probability that a randomly chosen individual has a height greater than 68 inches. Shall I draw that? Let's draw that so we understand what we're looking at. Okay. I'll bring this back up here again. Mean of 68 inches and a standard deviation of 4 inches. Okay, mean, mu, equals 68 inches. Standard deviation equals 4 inches. So this is 68 and a standard deviation of 4 inches. Okay, so first question. What's the probability that a randomly chosen individual from this population has a height greater than 68 inches? Right, 50%, right? Okay, these are all the people that have a height greater than 68 inches. Next question. Between 64 and 72. Let's see, where's 60? Let's take a look at down here at these z-scores, right? One standard deviation above the mean is going to be 72. Two standard deviations in the mean is going to be 76. One standard deviation below is going to be 64. Two standard deviations below is going to be 60. So what's the probability of having a height between 64 and 72 inches? 64 and 72? Right, it's both sides, right? If I had said between 68 and 64, that would have been 34%, right? Okay. Between 60 and 76 inches. Okay, 95%, right? Two standard deviations above to two standard deviations above. Okay, below. Okay, let me undo this. Let me see if I can avoid redoing all this. Okay, next one. Assume that the heights of the adult Caucasian women have a mean of 63 inches and a standard deviation of 3 inches. Well, this time Same normal distribution. It says it's normal distribution. Mu is 63 inches, I said, and standard deviation is 3 inches. Okay, just to go over this, the mean is going to be 63. One standard deviation above is going to be 66. Two above is going to be 69. One below is going to be 60. Two below is going to be 57. Okay, so let's take a look at what they're asking us. Probably it's greater than 63 inches. Again, yeah, 50%. Greater than 66 inches. Well, it's a little bit of a curve there, right? What's the probability of having a height greater than 66 inches? In other words, this area here, greater than 66. How are we going to determine what that is? Well, we know the area in here is 68%. And the area between the mean and 66 is 34. And we know that anything above the mean is 50%. So if this is 34, what's left?
16.
16. Exactly 16? Remember, we're using the empirical formula, right? So it's an estimate, not exactly 16. If we wanted to know exactly, what would we do? We'd go to the z-table, right? And we're going to take a look at the z-table in a little while. Matter of fact, let's take a quick look at it right now. I just told you that one standard deviation above the mean, right, represented, let's see, this is 68%, let's see, 34% here and 50% below here. So if I take a z-score of 1, the area below here, according to the empirical formula, is let's see, 50 plus 34 is going to be 84%. What is it in real life? Let's see that. Let's see our z-table. Where'd it go? Did I close it? I don't think I closed it. Let me go back to this z-table. Agresti. Okay, positive 1. Z-score of 1.00 is actually not 84%. It's 84.13%, 0.8413, if we're looking at a probability of 1. Right, so it's a little bit different. Let's take a look at another one. Remember we said that one standard deviation below the mean is going to be, let's see, two standard deviations below the mean to two standard deviations above the mean is going to be 95%. What percent, that leaves what on the outside of the lower end and outside of the upper end? That leaves 2.5% on each side, right? Let's see if that's really true. Let's take a look at a z-score of -2 and -2, right, which is going to be the area below, it's going to give us the area below a z-score of 2. Okay, let's see. -2.0, it's not 2.5, it's 2.28, right? I'm sorry, say again? No, negative, I want two standard deviations below to two standard deviations above, right? So the area below two standard deviations should be 2.5% according to the empirical rule, but it's not, it's 2.25% roughly. Well, what is the real value that would give us 2.5% below and 2.5% above? Well, I got to look in the areas here, and let's look where the area is 0.25. Here it is right here. Right? So what is that area? That area is -1.96. Okay, let's look at the high end where the area below that point would be 97.5%, leaving 2.5% out on the end. Okay, where would that be? Let's see, 97.5. 97.5. Here we go right here. And what is that value? What's z-score for the value where only 2.5% is above that point? It's 1.96. That shouldn't be a surprise, right? Because they're symmetrical, right? So in real life, 95% of the population is between 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. By the end of this semester, you're going to hate that number. I guarantee it, right? Because it's going to come up over and over again because most of the time we're going to be looking to demonstrate that something is within 95% chance of being true, or less than 5% chance of being true outside of that 95%, right? That's really what a lot of what we're going to be doing for the rest of the semester is going to be all about. Okay, let's go back to our problems. Okay, adult Caucasian woman greater than 6. Okay, greater than 66 inches was where we were working, right? And we decided that greater than 66 inches represented 84%. That's how we got into this whole thing, right? Okay, but that's okay because we're using only the empirical formula. Less than 60 inches. If I go back here, less than 60 inches means less than -1 standard deviation, correct? So what area is represented by less than 60? Okay, what area is that? Well, how much? Okay, what's the area between the mean and 60? 1 standard deviation below the mean? 34, and that would leave 16, right? Or roughly 16%. Sure.
Someone had a question online.
Oh, I'm sorry. Oh, thank you. Oh, you guys can see that, hey? Why doesn't the z-score table match the empirical rule? Because the empirical rule is an estimate. It's intended to be an estimate. It's a general principle that we can use to just estimate or judge, make a general judgment as to how a distribution is spread out. Okay, it's not intended to be an exact measurement. This, our z-table, or we're about to look at Excel, those are things that we're going to use when we want to get an exact measurement. But the empirical rule is going to come in handy for us because as you go on, what's that? In other words, when we say that 95% of the values are between 2 standard deviations below and 2 standard deviations above, it's really 1.96. A z-score of 1.96, not a z-score of 2. It's an estimate. The empirical rule is an estimate of the distribution, not the exact distribution. Okay?
Yeah.
All right.
I was thinking maybe they're asking like between 2 bounds as opposed to like to the left, like
No. We're just talking about how, like, if you really want to know what the exact value is, you really need to look at the table. Okay, does that help, Annie? Go Nationals. Okay. All right, good. So at any rate, let's go on to the next one, see what we can do with the next one. Gestation time for humans has a mean of 266 days and a standard deviation of 25. Again, in all of these things, all these examples, we're making the assumption that it's a normal distribution. If you go on to epidemiology and find out that it turns out not to be a normal distribution, don't come back and complain. We're just using these as exercises. Gestation for humans has a mean of 266 and a standard deviation of 25. Okay, let's draw that one. I'm gonna erase these so I can reuse this. Oops, I gotta click in here. Okay. Okay, our mean. Oops. Our mean is 266. And our standard deviation is, what did I say it was? 25. Okay, so our mean is 266. And our standard deviation to 25 above that, 1 standard deviation. Okay, what percentage of pregnancies would you expect to be greater than 291 days? Well, let's see. Now, these numbers are getting a little bit more complicated. So why don't we use our z-score formula? X minus mu over sigma, right? So what is X? The value that we're interested in, which was 291 days. 291 days minus 266 over the standard deviation, which is 25. That's, if I'm not wrong, that's 25 over 25, or 1 standard deviation. And the question is asking what percentage are below that or above that? Greater than 291 days. Okay, so if we use our empirical formula, whoops, here's our 295. Here's our empirical formula. Then we have 50% in here. We got 34% here, leaving 16%, right? Now, let's use our z table and see if we get the same answer, or at least close to the same answer. So we're looking for a z-score of 1, positive 1. Z-score positive 1 has an area 1.00, has an area of 84.13% or 0.8413. So this area is 8.8413. So what does that leave here? That leaves 0.1587, right? Pretty close to 16%, but not exactly 16%, right? There's a difference between our empirical rule and what the actual value in the z table is going to be. But if I'm taking a test and I see that I look at this very quickly, and I do my calculation with my z table, and I say, okay, I say an easy mistake to be made might be, okay, it's 73.7%. I might say, I might say to myself, that don't make any sense to me because it's one standard deviation. This should be 16% or so. And how did I get 84%? Right? Well, I got 84% because I forgot that I'm looking for the area above, right? Maybe I did something wrong in my calculations, reversed the mean and the value and so on and so forth. Knowing the empirical rule, keeping it in the back of your head will help you avoid making mistakes when you do calculations using Excel and or the table. Okay, or even SPSS when we eventually get around to using that for some of this work. Okay, so let's look at the next one. So the empirical formula has value. Okay, less than 241 days. Again, if I'm going to use the formula, Z is equal to 241 minus 266 over 25, and that's equal to -1. Did I really need to do that? Well, as these numbers get more complicated, it helps to use the formula because it makes it harder for us to make an error. You could have also glanced at that and said, oh, that's 25, and I know the standard deviation is 25, so I don't really have that hard a time figuring this out. Less than 241 days or greater than 291. I'm going to ask you to do that. Less than 241 or greater than, what was it, 262, what was the value? 291? What's the probability of having randomly choosing a pregnancy and finding that the gestation period was less than 241 days or more than 291? How would you answer that? What's the probability of its being less than 241? 16%, right? Because one standard deviation. What's the probability of it being greater than 291? 16%. What's the probability of its being less than 241 or greater than 291? In other words, both of those satisfy my outcome. So it'd be 32%, right? Since they both, I add the probabilities together because both of them is going to satisfy the outcome that I'm looking for. Okay? All right. So it's 7:27. I was going to take a break, but might as well plow through. Okay, solve the following problems using the Z table or Excel. So let's give Excel a try now when we take a look at these next few problems. Okay, so assume the heights of adult U.S. women have a mean of 63 inches and a standard deviation of 2 inches. I may, if it's really ridiculously simple, I may make some adjustments there. Okay, so in this case, we're looking at mean of, what was it, 63? 63 inches is the mean, and the standard deviation is 2. Okay, probability less than 63, we know that, 50%. Less than 62 inches. What's the z-score of 62 inches? Right? Should I do it this way? Z is equal to x minus mu over sigma. Z is equal to, what's x? The value we're looking for, the z-score of? That's our 62, right? Minus the mean is 63 over the standard deviation 2. What's this equal to? Negative 0.5. Okay, so if I want to know what's the probability of, what was it? Of being less than 62 inches, that would be the area to the left of that, right? We could go to our z table. Okay, less than 0.05, less than 0.5 rather. 0.5, what's that probability? 0.50? It's about 31%, right? 30.30, that's 30.85 or 0.3085. Let's use Excel to do the same thing. I'm going to open up Excel. How you guys doing online? Okay, I guess so. You're either asleep or you're doing okay. Okay, good. Glad to hear it. Oh, here we go. I'll do this way. Okay, so I'm going to click in here, and what are we looking for? We're looking for values that represent the z-score in a normal distribution. I'm going to type in an equal sign. I'm going to just wing it and say normal. Oh, look at all these. Norm dist, norm dot dist, so on and so forth. You can use norm dot dist or you can use norm dist. I'm going to put parentheses in, and it's going to give me the values that I may be interested that it's going to want to to come up with a value. And it's going to ask me for x, the mean, the standard deviation, then it asks something cumulative. Okay, we'll get to that in a second. So in our problem, what was the value x? 62, right? Right? Comma, what was the mean? 63. Comma, what was the standard deviation? 2. I'm going to do another comma. Now I'm going to cumulative. Cumulative is either going to be true or false or yes or no. Cumulative, what it's asking us, do I want the value of that exact number, 62? Or do I want the area below 62, the area of the curve up to 62? What did we say about the meaning of that exact value? It's a straight line, so it has no area, really has no meaning for what we want to use it for. So I'm never, ever going to use false for cumulative for this function. Why does Excel put that in there? I have no clue.
It returns
right?
something different if you put false there. It returns what the area would be if it were 1 unit wide.
Okay, yeah.
So it won't give you 0.
Okay, so I'm going to type in true. Yeah, but again, that has even less meaning. So at any rate, so what was the value that we estimated when we used the z-table? 30.84, right? 0.3084. Excel just gave us that same area. Okay, there's another version of this equal norm dot dist. Okay, and it basically gives you the same thing. Let's see what we wind up with here. 62, comma, 63, comma, 2, comma, true.
So you always have to put true?
Yeah, you have to put the true in there. Like I said, no one uses it any other way, but there are other functions that have that same format. So the only thing I can think of is that that's there because they're maintaining that format for putting the data in. Okay, but you would never use anything but true.
I guess one thing you might use it for is if you wanted to plot one of those.
Oh, if you wanted to actually find all the values.
Yeah,
If you're going to actually use Excel, and you can use Excel that way because you can make a series of numbers a mile long, then have it calculate all those values, and then even plot them. So, I mean, Excel is kind of a perfect instrument to create a z-table from if you couldn't find one, if you wanted to make your own. Right? So, but this is the way we would typically use this. Now, let me ask you something. What if I wanted to know what the value would have to be that would give me an area below that value for that z-score of 30.84%. In other words, maybe I want to do it the other way. I have an area. What's the probability, what's the value that I have to have for height that would give me a probability of 30.84% of having someone below that height? Well, we have something called norm inverse.
But your value is going to be a range, right?
No, my value, it's going to be a value, and that value is going to be the probability of having 30% chance of having below that value. Okay, you can have a value that's a range also, because then you have to do two calculations. Okay, so what's it going to be? It's going to be the probability times the mean, and then the mean, and then the standard deviation. What's the probability that we're interested in? We're looking at the probability of randomly picking someone out that's lower than that number of 30.84%, comma, the mean is 63, and our standard deviation is 2. And what is the value that'll do that for us? It's 62. We just did the exact opposite using Excel of what we had done to calculate that area. We took the area and calculated what the height has to be to have that probability of finding someone of that height or less. Okay, so a little confusing, right? As we're going through this, they get a little complicated, they get a little bit more confusing. And I tried to give you enough of these to go through this whole sequence. And maybe when, later on, you can download this and give this a try. Again, go through this whole sequence. Okay.
Also, you could just find the norm div and subtract it from 1. Or norm dist, right? And subtract it from 1.
The norm dist. Well, the norm dist subtracted from 1 would be the probability of somebody having a height greater than that, right? Norm dist gave us 30%. So 1 minus norm dist would give us 70%, right? That would be the probability of answering another question, which is, what's the probability of having someone whose height is greater than 62 in this population? And that's...
Sorry, so that's what, as far as the next question.
Oh, okay. Oh, you got ahead of us. What's the probability of having, yeah, well, I see what you're driving at. Yes, you're right. What percentage of women would you expect to have a mean height greater than 66 inches? Okay, well, that's going to get a little bit more complicated, isn't it? Okay, we're looking for the probability of having a height of greater than 66 inches. So here's 66 inches. Okay, here's 66 inches. So we're looking for this area here. So in order to calculate this area here, there's a couple of ways I could do this. If I want to use a table, I need to know what the z-score is for that value, right? So what is that value? What is that height that what is the percentage of people above that height? Okay, or the probability of picking a person above that height, that area. Okay, well, let's see, 66, if I calculate my z-score, it's going to be equal to x, which is 66, minus 63, over 2, our standard deviation. So that's going to be 1.5, plus 1.5. So if I go to my table and look up 1.5, okay, 1.50 is 93.32, 0.9332. So what area is that? I just figured out 93.2. That's the area below, isn't it? Because it's always going to give us the area below that point. Not all tables do it that way. Some tables give you the area between a value and the mean. Some give you a value to the right. But so you have to look on the individual table that you're using. Either use the same table all the time so you don't have to deal with it, or just be careful of how that particular table works. In a minute, I'll give you. So in other words, this is going to be 90.93. I forgot what it was, 0.933, say roughly. So what's the area above that value, 66? It's going to be 1 minus 0.933, or 0.47. No, 0.57, right? 0.57. 0.67? 0.57. 0.67. 0.67. Right? Okay, 0.067. or about 6.7%. Okay, so that's where that 1 minus comes in. And if you were going to do it in Excel, to find that area, let's find Excel again. Okay, it's going to be equal to norm dist, parentheses, the value was 66, the mean was 63, comma, standard deviation was 2, cumulative is true, gives us that whole area to the left of 66. The area to the left of 66 comes out to be 0.933, and the value we're actually looking for is the area above that, so it's going to be 1 minus 0.93, or 0.067, I think we estimated
So we
that.
could also use norm inverse there.
What does norm inverse do for us? Norm inverse, parentheses, what's it going to give us? Probability. The probability of getting this value, right? Now, the only problem is that value is on the wrong side, isn't it? Let me see what I get when I do this. 63, right? Comma.
What does,
It's going to work out okay anyway, Ray, you're right. Okay, 2, comma, parentheses. Oops, I made a mistake. Try this again. Equal norm inverse. Probability is going to be 0.06, comma, mean is 63, comma, standard deviation is 2. Well, I'm going to get a number 60. Why am I getting a number 60? Because it's always looking at that value to the left of the, in other words, that 6% is below that value. For norm inverse and norm dist, they're always looking from that point to the left. That's why it's cumulative. I really should have put in here, what I really should have put in here was this other probability equals 1 minus 6.7% is equal to norm inverse, the value which gives me an area to the left of 93%, comma, 63 is the mean, and 2 is the standard deviation to get 66, the value we're looking for. Okay? Little tricky, but you want to know something. If you kept the empirical formula in your head and realized and sketched it, if you sketch it and kind of keep the empirical formula in the back of your head, it's tough to make a big mistake. Right? It's tough to make a mega mistake. It would be very easy to just put down, 60 is the right answer. Right? That would have been the wrong answer, but we know that's on the wrong side of the mean. Right? Because if we sketched it, we would see it immediately that we got the wrong number for the value that would give us the 7% is above that value, right? Just by sketching it. So sketching it really helps, and keeping the empirical formula in the back of your mind really helps. Okay, so we're at 741. I just want to quickly go and kind of skip